All right, we've talked about most of the atmospheric variables up until now and how they influence each other. And now we're going to culminate it all with wind and a little bit about the weather. Wind is the motion of air. So when air moves or when we see it, we feel it rustling the leaves or whatever, that's wind. And there are lots of factors that influence the air motion. So we're going to discuss those right now and go into that area. So what forces actually control speed and direction of the wind? Well, first let's think about wind. It's a motion of air measured relative to the Earth's surface. What the heck does that mean? Well, where you are, that breeze, those air parcels or whatever have moved towards you from somewhere, either from the east, west, north, south, and how fast they got there. So it's the motion of that parcel of air relative to where it's sitting on the earth, where you're sitting at on the earth. So if it's coming out of the north, say it's coming off of Lake Erie if you're out Mount Vernon or whatever, and then it's coming down from the north, that air parcel is going to have some characteristics from up there being pushed that way. And one of the interesting things about wind, it has a direction and a speed. So that's why it's known as a vector. It has two quantities that measure it. Temperature is only one. It's a temperature. Pressure is only one. Moisture is only one. But wind is two. We want to know where the wind's coming from and how fast is it getting there. So there are a lot of forces that affect an air parcel and cause it to move. So force is very simply the mass of the air. We talked about that in terms of density. It's just, how many molecules are there causing it to weigh something. And we're putting an acceleration on that. Well, you think about your car. If you're sitting in the parking lot and you want to back out, you step on the gas, provides an acceleration to pull your car out of the parking space. That's what happens with air. There's a force that's being applied. That force that moved you from your parking space out is a force. And there are similar forces that impact an air parcel. One of those is pressure gradient. We talked about pressure a while ago. The tighter the air pressure is together, the stronger the pressure gradient. Think about it as if you were on a steep mountain slope and the contours on that slope were very close together. It sure makes it tough to go uphill, but pretty easy to go downhill. Matter of fact, you might even fall and slip and move real fast downhill. Well, air hates to be a vacuum. So nature, God has created it so that we don't have vacuums on Earth. So anytime air pressure is very tight, changes very quickly, the pressure at the highest areas are going to move towards the lowest areas. The closer the lines are together, the faster that air parcel is going to want to move down that slope. So they're always moving from high to low. The atmosphere might look like a mountain in a way if you tried to think about high pressure being a little bit higher up and more air there, and low pressure being less air. And the mountains are always going to be trying to fill in the valleys. So that's what an air parcel is doing with the pressure gradient. Now there's something else called centripetal force. It's center-seeking force. When you go around the corner in your car, what's holding you, allowing you to go around that corner without flying off to the side of the road? It's something called centripetal force. It holds you into that curve. It allows you to go around the curve. So it's always related to some kind of curved motion. And you think about it, on a high or low pressure, there is curves. The wind flows in a curved motion around those systems. So there is centripetal force that is acting on that air parcel. Another force is Coriolis effect. It only happens on a rotating Earth. It really isn't a force, but the fact that we have a rotating Earth, it actually exists. But what is it? Well, take a look at this map here. You have right here in the center of the US at one moment in time, all of a sudden, remember the Earth is rotating, and yeah, it's going to rotate a lot faster down by the equator than up to the north. So what happens is that same location relative to its south has moved. There's been a force exerted on that location, believe it or not, pushing the air to the right in the northern hemisphere and the air to the left in the southern hemisphere. And that is the Coriolis effect. The closer you get to the North Pole, it hardly moves, right? But it moves much further down here. But that hardly motion there causes there to be tremendous force. Whereas down here, there's less and less force the closer you get to the equator. The Coriolis effect at the equator is actually zero, where at the North Pole, it reaches a maximum. So there is a force called Coriolis effect. Now we've got that. And you can see how it deflects air parcels to the right. The further north you are, the more they go to the right. The further south you are in the northern hemisphere, the less they go to the right. Friction is another force. Think about it. If the air is going over a mountain, that air is having a tough time getting over that mountain, right? That's friction. Or if it's very rocky surface or whatever, and the air is moving along over it, you can almost feel bumps if you were in an airplane as you're flying, turbulence over some rocky mountains or some areas like that. And over water, on the other hand, there's not a lot of friction. Water is relatively smooth. Even with the waves in it, it's relatively smooth. So the friction is less over water than over land. Friction really only takes into account in the lowest 3 to 5,000 feet of the atmosphere. Generally, that's the area you're going to find the most friction. There is things like turbulence because we do have a fluid. The atmosphere is a fluid that does occur up higher up, and you can feel it sometimes, eddy motion and all that. But that is turbulence. Gravity is another force that acts on air. It's always pulling it towards the Earth. So there is a gravitational effect. It doesn't want to let the air get away. It's always accelerating downward at 9.8 meters per second. So now, just to review, we have pressure gradient in the horizontal, centripetal force, which is just curved force, Coriolis effect due to the Earth's rotation, friction, and finally gravity. Those are the main forces that act. So let's think of the pressure gradient in the vertical. We know in the vertical, pressure decreases much faster than it does in a horizontal pressure. So if it's decreasing so quickly in the vertical, well, wouldn't that air parcel want to go flying upwards and leave the Earth? But here's the thing. We have gravity pulling that air parcel down. So there's a balance on that air parcel between the pressure gradient force in the vertical and gravity pulling it down. It causes that air parcel to just stay right where it is. If nothing else is acting on that air parcel will be perfectly still. And that's the hydrostatic equilibrium. However, there is some imbalances that occur, and they can cause the air parcel to move upwards or downwards. But when it's in true hydrostatic equilibrium, say the air parcel hit a mountain, it'll move up. Comes down the other side, it'll move down. But the hydrostatic equilibrium says that it's not accelerating, it's just slowly moving up. Once it's been pushed, it's slowly moving down once it's been pushed down. So there's no acceleration with a hydrostatic equilibrium. Geostrophic wind. All right, meteorologists like to look at the wind in different ways to try to make it as simple as possible. So aloft, it's easy to just look at wind that has just pressure gradient and Coriolis effect. And when they balance, and eventually they do, you'll see a straight line motion of an air parcel. It's not still, it's moving. So the more pressure gradient force, the more this Coriolis effect is going to impact it, because the stronger the wind, the stronger the Coriolis effect is. So you get a very nice straight line. But now you get these curves. high pressure, low pressure. Wind's going to want to flow in a curve. What happens then? Centripetal force is added in. So gradient wind is just centripetal force, Coriolis effect, and horizontal pressure gradient. It's 3 terms instead of 2. But it allows us to define how the wind's going to move around a high pressure or a low pressure. Finally, we add friction. Friction just reduces the wind effect. It slows wind down. So by slowing it down, it actually reduces the Coriolis effect a little bit and allows the wind to turn away from high pressure and towards low pressure. So what happens is, if you look at a map, you will see winds blowing slightly away from a high pressure system around it and slightly towards low pressure systems. And here you can actually see that if you were to look and follow the mix. The closer you get to the low, the more and more they come in towards the center of it. The further away from the low, the further out they go. And the high pressure is exactly the opposite. One of the things about wind, too, is the air is always a fluid, so it's always what impacts it at one part is going to impact it at another part. For example, if you have horizontal convergence aloft, winds coming together, that's going to push that air down. It's going to want to sink. Well, if it's going down, you're going to wind up at the bottom, causing horizontal divergence. And that is what actually forms an anticyclone or high pressure system. So when you look at high pressure systems and see them on the weather map, you're actually getting horizontal convergence aloft and horizontal divergence at the surface. And if that air parcel is sinking, it's warming, means it's becoming drier, right? We learned that the other week with relative humidity. So that's why you don't have clouds in a high pressure system. But in a low pressure system, you have horizontal convergence at the surface and divergence aloft. So what happens is that air parcel is rising, it's cooling faster, it's condensing. Therefore, you're getting the clouds and your precipitation. That's why you have the stormy weather systems. There are other things that can cause divergence or convergence. Sometimes maybe a rough surface, winds blowing along it and they hit a lake. All of a sudden, the winds take off across the water. They're moving much faster. So you wind up with divergent sinking air. Other times, however, say you have a sea breeze, the wind is coming in from the water where it doesn't have much friction. It hits the land, has a lot of friction. It slows down. The air is piling into it from behind. Where is it going to go? It's going to go upwards. You wind up with, you now implied or enforced upward motion. That's why you get the clouds along a sea breeze front. So when the air is coming from the water to the land, it's going to be forced upwards. When the air is coming from the land to the water at nighttime, for example, it's going to go the other way. And there are different planetary scales of motion. We're going to get into these next week. Really in big time. There are whole large wind fields that circle the globe. There are synoptic scale systems that we're used to talking about, like extratropical cyclones, which are just low pressure systems. And there are mesoscale systems, that thunderstorms or sea breezes, and then even microscales, way down to tornadoes, in the areas of weather systems that just cover a few blocks. So all that we'll get into next week. So let's just take a quick peek at some wind today. Well, here is a surface weather map. Here's some wind around high pressure. Pressure gradients, not too bad over here. And here you have 20 knots of wind. Right in here. Oh yeah, look at it. It's going towards low pressure, away from high pressure. So it's following the rules we just learned. Again, up here, high pressure, pushing towards the low and out of the high. You're going to have drier air up here. Kind of divergence is occurring. You're going to have wetter air down here because convergence, air is being lifted. If you wanted to look at this, say you wanted to look at where friction is impacting. Friction is causing, the air is mixing, we'll say, and it's causing a uniformity temperature drop very close to dry adiabatic typically. And it occurs in what they call the boundary layer. In his case at Oklahoma City yesterday afternoon, the boundary layer went up to about 1 kilometer. So in this area, if you were flying an aircraft landing, you would have more turbulence down towards the ground because there's a lot of friction going on. Once you got above that, the turbulence would diminish as far as that friction caused turbulence. Now, eddy turbulence and all that could occur at different places. So this is the area that friction from the ground is influencing. So all the way up to about 3,000, 4,000 feet. Once you go above that, you get away from that. So let's take a look above that. Here's 850 millibars. We're kind of above most of the friction influence here. The winds are stronger. Friction slows wind down. And, for example, right here you have your pressure gradient and your Coriolis force exactly balanced. So you have geostrophic wind right here. And if you were to look at 300 millibars, go way up above it, you can see it's even much stronger winds. Again, you don't have any friction. Pressure gradient is still strong. And here's your divergence. This is area of yellowish colors here is strong divergence. And yes, it has been raining all night at my house. So it's just now ending. And this divergence, if you go back to the surface map, the latest map, low pressure. So that divergence caused convergence at the surface and actually generated a low pressure system. So this is what the wind's all about. So I hope you got something out of this. Please don't hesitate to ask any questions.